It's my pleasure to introduce Gaël Varoquaux. I will give a short introduction. So Gaël Varoquaux is a research director at INRIA, University Paris-Saclay, and Institut Polytechnique of Paris. You are at the crossroads of the two. Gaël has an impressive career already. He started as a student of École Normale in quantum physics, and he did his PhD with Alain Aspect, Nobel Prize. And Gaël was also interested by computational aspects, and at some point he wanted to work at INRIA and got very much interested by machine learning. And in a very simple way, he simply created and co-founded one of the tools which is the most used machine learning library, scikit-learn. Is one of the co-founder. Okay, so maybe you know this tool. And also, Gaël has developed research in machine learning, combining interest in health application, in methodological and theoretical machine learning, with always an interest in algorithm and working in practice with difficult data, data which are, we can say, dirty, so, you know, with noisy data, corrupted by some contamination, and also missing data. But you have worked in many other topics. I won't describe them, and now I give you the floor, Gaël.
Thank you very much. Which phone is this? Is this yours? Yes. Okay, so the real story, by the way, about my career is I have no idea the fuck I'm doing. That's absolutely true. I'm basically interested in too many things, and I get clever people to explain me things and work together, and everything I do is actually fairly simple. I'm not lying, by the way, and you'll see. It's actually fairly simple, but it's more tied to, mostly it's about bridging things, right? So it's about, you know, taking applied problems and looking at whether we can formalize them in a good way, and then, you know, doing some simple stuff on the formalization, or, you know, discussing with people and learning about all kind of different things, and then applying them to a given set of applications. And so maybe you'll really see that, you know, my talk doesn't really have a lot of complicated math at all. Okay. So, given the topic of the workshop around uncertainty, I wanted to talk about some work that we've been doing. The work has really been led by Alexandre Pérez Lebel, a former grad student of mine, and Marine Le Morvan, a PI in the group. And really, you know, the setting is, you know, these days, modern AI really moves forward by doing all kind of crazy things. You know, it's really hard to understand I mean, we post-hoc understand things like layer normalization or gradient clipping. I still don't understand. I mean, I have some understanding of cosine scheduling, but honestly, don't get me. Don't ask me too many questions on this. And you know, we claim we do backprop, but we keep doing things that are not backprop, that are, you know, basically kludging some form of gradient-like descent. But the thing is, it works. I mean, it's been incredibly successful, and you know, we can think that we'd like to have probabilistic modeling in the good old way of framing things, but it works. It powers things like image generation or large language models, and it does really cool things. Does it though? You know, you ask questions to an LLM, you get answers that are of, you know, varying quality. I mean, this answer tells me that Einstein was born in the German Empire on January 14th, 1879. I'm pretty sure that date is wrong. LLMs are pretty bad with dates. I don't know if he grew up in Germany, but I'm pretty convinced he did not do his PhD at Humboldt University, Berlin. So, I mean, LLMs are completely incapable of telling us when they're right or they're wrong. So what we would ideally like, is maybe, people who do statistics, is some form of uncertainty quantification on this. So ideally, and I'm more talking from an applied perspective, this really matters. Ideally, we should be able to flag parts of an answer that are more likely to be correct and more likely to be incorrect. And this isn't really done in production so far as I know. So when I'm saying this, by the way, I'm maybe saying this in a way that's obvious to the audience, but I'm not sure it's obvious to all the application settings. And it's actually bloody hard. Also, I want to stress that, so I've put the typical, poster illustration of uncertainty quantification, which is, probably a Gaussian process. But in many problems, this isn't the right mental picture to have, because many of the problems we have discrete outcomes. The previous problem about the LM, things are right or wrong. Or for dates, we could say there's a continuity. So the real mental picture to have is that of discrete outcomes, often binary outcomes. And in my experience, a lot of the tools don't work, or they work in theory, but I don't know how to use them. One example is conformal prediction. I mean, there is some conformal prediction on classifiers. I've just never been able to do anything meaningful with it. The idea of covering coverage stats when you have, two outcomes, I just can't do something useful with it. Maybe it's just me, by the way. Anyhow, I want to stress, and this is going to be really important, that we have discrete outcomes. Typically, it's zeros and one. We never observe the probability that we're interested in, and we're going to use tools that actually work in those settings. And so what people have been doing, and once again, maybe I'm going in things that are obvious for the audience, but I think it's worth going through the state of the practice. What people have been doing is that they've been defining uncertainty bins. Well, so your black box outputs something that's continuous that you would like to be some form of probability of class 1, for instance. And so you define bins, and then you count error rates. And so doing this, gets a plot of the fraction of positive as a function of the predicted probability. And this is known as the calibration. This is a calibration curve. And this is what people are mostly using, vast majority. And if if we have the predicted probability that is below the diagonal, then the classifier is said to be overconfident, and if it above, it's underconfident. And I want to stress that, so when the field is a mess, because the most definitions of calibrations are this, at least in machine learning. When people use the term calibration in writing, they mean my probability approximate the true posteriors. And there's kind of a leap between the two. And maybe this is obvious for the audience, but I've seen this leap in so many papers that are, as a consequence, incorrect in some way, including by people who are very solid researchers. Okay, but why do we want probabilities? Maybe it's important to say this, and the idea being that you're doing a black box, or you have a black box, and this black box can be thought as a forecast. It can be thought as something that outputs a number that will be used, and having this number, this y hat estimated y, close to p of y, enables a separation of concern between the person who actually computes the number and the user. I'll come back to this, but probabilities allow you to design a box without knowing how it's being used, because it's the best you can do. Okay? So this has led to a conventional wisdom in forecasting is that we want good probabilities of the output of Y. And this actually leads to the notion of calibration. Now, if I go back to the example of large language models, the plot that I was showing before, the calibration plot that I was showing before was a real calibration plot. And so what we did with Li Ho Cheng and Alexandre Pérez-Lebel is that we varied. So we asked this kind of question that I was asking earlier about, describing a real individual, but we varied the query nationality. And if you do this, you can see that the calibration curves are all over the place. Okay, so what I'm saying is that the calibration curve, and once again, maybe it's obvious, but it's worth stressing, is just an average result. In no way does it tell us anything about subgroups or about individuals. And in real life, we do find a lot of heterogeneity in the output of the black boxes that we use. Okay, so we want to capture probabilities, but ideally we would really like to be able to condition on certain features, just like the nationality. And so what we maybe would like to capture is a P of Y given X. And maybe for people in statistical machine learning, this seems obvious, but I want to say first it's not, and in practice, it's not what's done. Why is it not obvious? Well, what's X when I have an LLM? And then, what's X when I have weather forecast? This notion of X, when we write, a statistical machine learning paper, I say, let X in a vector space. Well, X doesn't exist in real life. It's a fantasy. And then second, once again, this is not what many people do when they compute the calibration curve. Okay, so one of the questions that I'd like to address in this talk is how far is a given predictor given f of x from p of y given x? Yes?
May I ask a very
Sure.
What is y in the case of the LLM? Is it sentences? Like, are you doing some form of...
That's a very good question. There's actually much more than what I'm discussing in terms of LLM. The why here, you actually need, it's a difficult question. You actually need to do all kind of engineering to, because you actually have a very complex output space to break it down in sub parts on which you can then test whether they're likely to be true or not. And this is actually complicated.
The example that you gave in the previous slide, what were the lines in that?
Yeah.
The calibration curves with the...
Yeah. Well, so you can see here that we're breaking sentence by sentence, and on sentence by sentence, we're checking whether the sentence is likely to be true. And so this is really what the calibration curves are doing here. And here also. And yes, indeed, there's actually a lot going on behind this. I'm more taking the formal problem than the applied problem here. But yes, you're correct. Thank you. Yeah, so I was saying that X is a complicated notion, but even Y is a complicated notion, which I will not cover here. Okay, so in my first part, I want to really look at that question. Given a predictor, and one thing I learned in this project, or later on, is that the notion, by the way, of predictor, which is f of x, by itself is already a framing that narrows the problem down, because it forces us to define x, and if I'm doing weather forecasting, I'm just going to acquire more data by putting more sensors. But I will not cover this. I will just cover the formal problem of I'm given f of x, and I want to know how close it is to p of y given x. And once again, I'm just going to restate things I've said, but in a more formal way. So we have the notion of calibration, which is a control on average, and the definition really is that probability estimates f of x are said to be calibrated if conditional on f of x given p, then the probability of y given equal to 1 is p. And that conditional of f of x on f of x given p is really important, right? It's, you know, if you want to have a picture, we have a feature space x, and we're really taking a level set of f of x given p. Now, it's important to have in mind that this notion of calibration was born without the notion of a feature space. Once again, if I'm doing weather forecasting, I don't have a fixed feature space. And so we in machine learning have framed the problem with a feature space, and so we inherited this notion of calibration and didn't really question it. Okay, so then formally I will define a calibration curve C as the function which associates the probability of y given 1 conditionally on f of x equal p. Okay, so it's really the curve here, it's a function, and then I will call calibrated estimates the composition of those two. And so here we have a tradition, which is the tradition in machine learning of, or not only in machine learning, of recalibration, which is to take probability estimates that are not calibrated, that are, for instance, overconfident and underconfident, and then correcting them. And I personally like to make the difference between calibration, which is the concept, and recalibration, which is the operation to fix this. I think the vocabularies have become a bit entangled. And so then there is the notion of calibration error, which is an expected error between f of x and the recalibrated error. Okay, and this is what the calibration curves that I've shown before estimate, and there's a beautiful literature that shows you that, well, you know, maybe you can do better than binning estimates on this. Okay, and then, you know, as I've mentioned before, you know, calibration is only an average quantity, and so we can have subgroups that are over and underconfident in the same population, and as I've shown you before with the example of nationalities in LLMs, we can have something that's calibrated on average, but there's clear structure in the error. And so calibration, it's really important to have in mind that calibration, we can have perfectly calibrated classifiers, but that are far from the optimal answer that we could get, which is p of y given x. Okay, and there's a big confusion that is done between the two over and over and over again. And one of the reasons that the confusion is done is that it's much, much easier to measure and compute calibration error than actually a distance to p of y given x. That's actually very hard. Okay, so to answer those questions, we're going to need mathematical concepts that are proper scoring rules, and there is a talk later on proper scoring rules, so I am not going to go in details. So what they provide is that they provide divergences between two distributions. And the reason why we need them is that we observe samples, and those samples are discrete, you know, they're 0 and 1, but we would like to control the underlying probabilities that are below those samples, which we never observe. And so the interesting thing about a strictly proper scoring rule is that it is minimum, though we don't know what minimum it reaches. It is minimum when the samples are drawn from the same distribution, okay? And so this is mathematically what we'll be using. And so then, so we'll be looking at the expected divergence between f of x and y. And this, by the way, this expected divergence between f of x and y is basically what we minimize when we train machine learning, when we train statistical machine learning. And so it can be decomposed, and this is work that we've done. This is work that's been done, for instance, by Cull and Flack. It can be decomposed in two terms. One, which is the aleatoric loss, which is if you take the best possible prediction, so P of y, you still, because you have a noise in y, you still have a divergence between P of y and y. It's just due to the intrinsic noise. And then you have another divergence, which is between your prediction, f of x, or the estimated P of y, and the optimal P of y, f star of x, okay? So it's the difference between, you decomposed in the difference between the predictor that you have and the ideal predictor, and the divergence between the ideal predictor and the observed labels, okay? And aleatoric loss, evaluating aleatoric loss is a way, for instance, of evaluating suboptimality. And if we, for instance, if we could actually evaluate those two, we could balance between acquiring more samples, which would reduce the epistemic loss because it would allow us to train better models, or acquiring more features, which would reduce the aleatoric loss. Okay? And so it's possible to go one step further and to decompose the epistemic loss between the calibration loss, which is what I've been discussing before, and something that people have called the grouping loss. Okay? So the calibration loss is fairly easy to estimate, and it's been estimated in many different work. We're going to focus on the grouping loss, and we're going to see how we can estimate it. So really, the grouping loss can be understood as a variance. In the paper with Alex Pérez-Lebel and Marine Morvan, we've written it this way, but really, one way I like to think about these decomposition between calibration and grouping losses, it's really a bias variance decomposition. Calibration is the bias, grouping loss is the variance. So really, if I were to plot the true probability as a function of the probability estimate, the grouping loss would really quantify the spread of true probabilities. Now, the challenge is that I do not have those true probabilities. So the estimation challenge is that I need to try to estimate this grouping loss, but only from the samples y that are discrete. And the way we're going to do this is that we're going to use the law of total variance. And so let me just walk you through the problem. So we're given an input space x, a function g of x, and our goal is to estimate a variance of g of x. And so one thing that we can do is that we can split the input space in a partition. We can compute the average of g on each part. And then, so we can compute the corresponding variance across the local averages. And when we do this, we have a remainder. We have everything that we haven't explained. It's the unaccounted for variance, and it's the gap between the local averages and J. And so really, the law of total variance is basically telling us that if we do local averages on bins, we're explaining only part of the variance. And we have a residual variance, and this residual variance is positive. That's really what we're going to be using. Okay, now we're going to apply this to our problem, and we're going to apply this on a level set where we're computing calibration before. So On the level set, we might have our oracle F star that varies. And this is this variation that creates grouping loss. Okay? We don't have access to F star, but it varies. But maybe this variation is canceling, the two parts of the variations are canceling each other, and so on average, it's calibrated. But we have unknown parts of the feature space where we're overconfident and underconfident. So what we have access to is we have access to samples. Okay, we have access to the observations, and so we can partition this level set as before and compute local averages of those samples of y. Okay, and those local averages of y estimate F star, and they estimate F star with estimation error that we can characterize. And so then we're gonna do this, and we're going to use the law of total variance to control the variance, and so the groupings. And so using the law of total variance, what we really get is that given a partition, we get a decomposition between explained variance, explained grouping loss, and residual variance, okay? So I've just applied the law of total variance to my problem of grouping loss. And what I'm telling you is if I choose a partition, I can explain part of the grouping loss. And now the name of the game is going to be to choose a good partition. Because if I choose a good partition, I will minimize the residual error, okay? And by this, I will get an estimate of the grouping loss that is a lower bound, okay? But if I make my residual, my unexplained grouping loss, then this lower bound is going to get close to the actual grouping loss, okay? What you're seeing here, by the way, is that we can only estimate, without any hypothesis on F star, we can only estimate lower bounds of the grouping loss. And in a sense, when you think of it, we can always find adversarial settings that will make it impossible to estimate a lower bound that comes close.
Just a question about the last term in your sum.
Mm-hmm.
Why don't you have an expectation there?
Oh, because I'm writing probably should have one. No, okay. There is an expectation. It's my V, my bold V is expected. It's just I don't have two expectations. In the first term, I actually have two expectations. Okay, but the bold V is an expected variance.
Okay.
Yeah. That's the whole problem, right? It's all there are expectations everywhere. Indeed. Okay, so it's a fairly natural result. If I do a partition, I'm estimating only part of the variance, but I can still estimate part of the variance with trivial plug-in estimators. Okay, and then the question is, how do I find a good partition? And we want to find this partition in a way that minimizes the unexplained variance. And it's something that we can do, for instance, with something like decision trees that are literally built to minimize a variance. If we give the decision trees with a squared loss. By the way, the results that we've done, they apply to squared loss, which is a Brier score in a proper scoring rule, but the same results also apply to other proper scoring rules like log loss, in which case you just need to change your loss in your decision tree. Okay? So really what we're doing is that we're using a decision tree to partition the residual error. We have a predictor, the predictor has an error, we're partitioning this residual error. Then we're computing local averages. And here we need to do something that's sometimes called honest trees, which is that we're splitting the data in two, and we're partitioning on half of the data and computing the local averages on the other half to avoid a bias. Then there's a bit more in the paper is that we can characterize a bias, small sample bias on the estimation of the variance because we have very few samples. Well, because when you have very few samples, you get bias. And so with this correcting term, what we find empirically is that it's actually better to build fairly deep trees that end up with fairly few samples per leaf. And this is how we get the best estimate of grouping loss. And so this correction error is quite important because it allows us to go quite deep. And with this, we get an estimate of grouping loss that we can we can prove is a lower bound. And then what we see empirically with is that it's a lower bound that can get quite close. Okay, but the real theoretical result only tells us it's a lower bound. Okay. Just one trick. What do you do when you have complex input space, text, images? Well, you use some low-dimensional representation of the complex input space. Elsewhere, your decision tree simply doesn't work. And in practice, what we do is that we use typically like the last layer of neural nets. Okay, so that solves the problem of complex input spaces. So we just use the embedding. Okay, just to show you, so when we did this, then the question was, is this just theory, or can we actually see it in real applications? And so the work that I've shown you with the nationality on the LLMs was done actually after, and that's a smoking gun evidence. But we started by looking on vision problems. One of the reasons that we did this is that over the last 5 to 10 years, there's been some form of back and forth with the calibration of modern neural networks, where there was a paper that showed that they were uncalibrated, then more modern architectures were calibrated, and the question is, basically, do these problems happen in real life or not? And it's worth, by the way, asking this question, because if you wanna get the best estimate of P of y given x, the best thing you can do is to minimize a proper scoring rule, and this is what modern machine learning does. I mean, 20 years ago we were using things like hinge losses, which are not strictly proper scoring rules. These days we use strictly proper scoring rules. So, if everything is done well, we shouldn't really have some form of grouping error. And just to cut a long story short, grouping error happens a lot when you have some form of mismatch between your training data and the data you apply on. So some form of distribution shift. And in the era of pre-trained models, it happens a lot. Okay, so we looked at some modern deep learning architectures that were pre-trained on ImageNet and evaluated on ImageNet R. And ImageNet R is this kind of thing where you have different type of images. And so, well, the first thing we can see, which actually surprised me, is that the calibration curve doesn't look too good. And this surprised me because it's fairly easy to fix. You recalibrate. But the second thing that we could see is that there was sometimes massive grouping loss. So what I'm showing you here, just for visualization purposes, is only 2 groups that are found from the data. But it really shows you that we have a substructure in this calibration diagram, and that we have some parts that are fairly underconfident and some parts that are fairly overconfident. And so from this, then we can actually compute the oh, by the way, the calibration error is really easy to fix. There are all kind of ways of fixing the calibration error, so you can really easily get to this picture, which is the network is calibrated on average, but you still have this structure, this brutal structure. And so then we looked at, we compared because the theory tells us that the total distance to the optimal probability decomposes in the grouping loss and the calibration loss, we can actually compare both of them. Okay? And so here we're looking at, this comparison, calibration loss versus grouping loss. What you can see is that typically, and this is something we've seen quite often, typically calibration loss is significantly larger. But you can really easily reduce it with recalibration. So it's significantly larger, but you can get rid of it easily. But then another thing that's quite interesting is that grouping loss varies a lot across architecture. And it doesn't vary in a way that's proportional to your calibration loss or to your overall error. So if you take, for instance, CovNext, it actually has a fairly small calibration loss and a fairly large grouping loss. But if you take Inception, it's the converse. Okay? Okay, so maybe, to summarize this part, people have been focusing on calibration error in machine learning because it's easy to measure. It is possible to estimate the remainder term. What we've done was, estimates based on bin. I'm sure it's possible to do better estimates. I'm surprised nobody has, as far as I know so far. And it's interesting because it allows to characterize the suboptimality of a given classifier with no hypothesis really on how it's built. Okay, so we've done this, and then the question is, people still weren't convinced. They were like, but I understand my grouping, my calibration error. It's really the error rate that I get, and in practice, that's all what matters to me. And we found that it was really hard to have a conversation around this because you need to go back to a natural application problem to see that it matters. And so what we did then is, okay, if we want to go one step further, and we want to say, well, this predictor that you have, this classifier that you have, is going to be used in a certain setting, and one way you might actually care about a final decision. So you're going to do decisions on this prediction, and how do the errors that you have incur suboptimal decisions. And so to do this, we basically need to loop to a decision theory. And one very, very simple example is the lottery ticket example. So you need to factor in notions of costs of actions, okay? And in the lottery ticket example, you have the you can really easily study this. A lottery ticket might cost $1 or £1 or €1, and might lead to a gain of $10 with a given probability p. Okay, and the question is, should you buy the lottery ticket? Yes or no? And so the way you answer this question is you basically do a table that computes your gains and losses for each choice. Did I buy? Did I not buy? Was the ticket a winning one or a losing one? And then you can compute your expected gains, and then you can compute the optimal decision, which is to buy or not to buy. And that's if the expected gains, the expected gains are positive, and it gives you a threshold on your probability. Okay, and back to the fact that this example that I've given, which is really standard decision theory. What if you have heterogeneity? If you have lottery ticket, you have good days and bad days, and so on some days you should be buying, on some days you shouldn't be buying. Well, ideally you'd like to separate this. So it's the same story. We're going to want more than an average control. We're going to want to have features that come in, and we're going to want, once again, to estimate P of y given x. Okay? So that's where we think grouping loss is going to become important. Okay, just to rewrite the above, we can rewrite the above in a general a utility framework, and this is very classic. And then you get a threshold that we're going to call T star that depends on the utility matrix, and the optimal decision is to choose action 1 if the probability of class 1 is above T star, and action 0 if the probability of class 1 is below T star. That's classic decision theory. And so a lot has been done on classic decision theory. What we were interested in is what if the probability that you have is not F star, but F. So an estimated probability that you hope is close to the real probability, but has some error. Okay? And as far as I know, very little has been done here. Okay, and our goal really is to quantify how suboptimal our decisions are based on this estimated probability of y. And I now have a lot of math, which I'm wondering whether I want to fully cover or not. I'm gonna if you accept, I'm not going to go through all the definitions and everything, and I'm going to focus on the intuitions. Okay. So I'll go a bit fast on some of these things. Maybe one thing. So we're going to be looking at expected utility, but we're going to separate point-wise expected utility, which is for a given sample. Conditional expected utility, which is for a given P and overall expected utility. And the most important is going to be conditional expected utility. And we're going to define the regret, both point-wise conditional and overall, as the difference between the expected utility of the optimal decision versus expected utility of the decision that we're actually making. Okay, and now the interesting thing, when do we have regret? So this is, once again, a plot that looks like a calibration plot, but it's an oracle plot. It's plotting the true probabilities as a function of the estimated one. And the optimal decision would be to threshold the true probabilities at T star, as I mentioned earlier. So the optimal decision allocates actions above and below the horizontal line. The actual decision that we're making uses our predicted probability, f of x, and does a threshold above and below. Okay? So it's separating the diagram in the other direction. And the regret is going to incur where the optimal decision and the actual decision disagree. So it's going to incur in the red areas and not in the green areas. And so what we could show in the paper is that actually the further away the true probability is from T star, the more regret we're going to pay in a linear way. So that's really what this lemma is telling us, is that the regret scales linearly, the point-wise regret, the regret for one sample scales linearly as a function of the distance between the true probability and the optimal threshold. And once again, the difficulty of all this is that it requires to have access to the true probabilities, which we don't. So we have access to two things. We have access to the calibration plot, which is the average, the bias in a sense, and we can quite clearly see that the more it goes in the red part, the more we're in trouble. And we have an estimate of the variance thanks to the previous work, okay? And same thing, well, more variance, more we're going to go into the red part. Okay, so we had before a decomposition of the epistemic loss. And so we'll show that we can also have a similar decomposition in terms of regret. And one way to see this is that if all you have is a calibration error, you can cancel it simply by either recalibrating or just shifting your threshold if the calibration error is monotonous, okay? So there's one part of the regret which you can fairly easily cancel by just shifting the threshold. If you don't shift the threshold, you get a corresponding error. And so as a consequence, you know, we have some form of ordering. So we have the oracle, which does the best expected utility. We have the recalibrated decision. And then we have our candidate, okay? And in terms of computing the calibration regret, it's really how much of the red part of the curve do we have. Now, the more difficult one is the grouping regret. And so the idea being, once I've accounted for the calibration regret, and suppose I have, for instance, a perfectly calibrated decision, because of the variance, it's still going to explore some of the red parts. Okay, and so can I estimate this? And so what we did is that we bounded it. Okay, and the idea being basically that the bigger your variance, the more you're going to explore the red part. Oh, an interesting thing from an intuitive perspective. What really matters is the variance close to the threshold, close to the optimal threshold. If you have variance on both ends, it really doesn't matter. So that's something, and unfortunately I don't think it's well written in the paper. That's a really important intuition that I got, is that what matters is really, you know, the variance that you have where you're going to make the decision. It's obvious, but then, I mean, I didn't have this intuition before. Okay, so really what we're going to do is that we're going to use this variance to bound, and really the idea is that, so we have if we're just looking at one slice, we have a random variant that has a given variance, and we're going to try to bound how much mass do we put on the penalty area, okay? And the idea being really that we're going to look at the worst case scenario for a given variance. And the worst case scenario is going to tell us the worst case penalty. And so as the variance increase, you know, worst case scenario gets with more and more mass on the side, getting to the point where all the mass is on the two sides. That's your absolute, you know, if you're given a given variance and a given mean, and you want to put absolutely no weight in the penalty area, then you end up having all the mass on two sides. Okay, when you get to this situation, if you increase the variance, then you start paying penalty, okay? And you start paying a penalty that goes up, and that's, once again, the worst case scenario that goes up with your variance. And we can do the other aspect, which is we can look at the best case scenario for a given variance. So minimizing the penalty, and so we get two bounds. Okay, one is a lower bound and one is an upper bound, maximum and minimum penalty, using this analysis. And okay, maybe the important aspect is that those two bounds, they're not particularly pretty, but they're written in terms of calibration error and grouping error. So they're written in terms of things that we can estimate. Okay? And they show you, by the way, that both calibration error and grouping error are important. All right. And then what we do, and that is not extremely elegant, is that we take as an estimator for the grouping regret, we take the mean of our upper bound and our lower bound. And this is what we'll be using. And then the question empirically that we want to ask is that are these things useful in practice? We've done all kind of all kind of upper bounding and lower bounding, and do we actually have things that are useful? And so the question that we asked, maybe I want to go back to, sorry, I want to go back way. Oh, that's the problem with animations. Well, okay. Anyhow, if you picture when I was showing on ConvNet and on the various black box estimators, if you picture, some had more calibration errors, some had more grouping error. And then the question is, given this, which one should I take to improve? Should I fine-tune one or another? And this is a real-life question because these days you go to Hugging Face Hub and you're going to have literally thousands of estimators. And which one, for a given application, do you want to fine-tune? And so what we did is that, so for a given expected utility, for a given utility matrix, so for a given set of costs, we estimated the expected fine-tuning gain. We estimated the regret, and then we compared it to the gain that we got by fine-tuning. Okay. And this is what we have here. And so first, the gain, expect the recalibration gain compared to the recalibration regret. Okay. And so what you can see is that the theory is, works really well. We can really predict very well what regret, what expected utility you gain by recalibration. And this, by the way, so the recalibration, the calibration loss regret actually is a much better predictor of the gain than things like the calibration error, the accuracy, the bias score, the AUC. And maybe it's obvious from the theory, but I can tell you this is what people are using to make their decision. And it goes back to the point that what really matters is what happens close to the optimal threshold. Okay, it's not everything on this curve matters. And then we looked at the full regret, and we looked at the fine-tuning gains. And so here we need to take the full regret in account. So we need to take both the grouping loss and the calibration loss. And so what you can see here is that the correlation isn't as good, but still the full regret is what correlates best. And a spoiler alert, we have a better estimator by now of the grouping loss, and that correlation improves a lot. Okay? Okay, so maybe, to wrap up a bit this, what we did here, which I think is important, is that we focused on measures that we can actually do in practice with the observed data without knowing anything about the predictor. And I think this is what's new. This hasn't been done a lot. And this is implemented in a Python package that's called GLEST for grouping loss estimate. I'm out of time, but I wanted to talk a bit about something else that I find is really exciting. So I'll just do a few words. I frame this in the setting of large language models. And then we can say, in this setting, people are doing crazy things. But in science, for instance, most of the data is tables, and I can do statistical modeling rather than complex models. And without going into details, another sort of stuff that we've been doing in my group that I'm really excited about is actually building. Well, I have a love-hate relationship with this work, but it's basically building really complex models that work really well on tables. And there are two directions which I will not cover. One is we bake in really rich priors using transformers as general algorithm approximators. And so we basically teach transformers to predict. And that was pioneered by the group of Frank Hutter in Freiburg with a TAP PFN line of work. And the other one, so I'm skipping all this, and the other one is that we bake in knowledge and semantic, because a lot of the tables that we work in actually implicitly come in with knowledge and semantic. And that's a different line of work that I don't want to talk too much about. Okay, thank you very much.
Thank you very much for the great talk. So now it's time for questions.
I was just wondering if you could expand on the intuition behind, you mentioned that grouping error was associated with kind of distributional shift. In my mind, I'm thinking that would also incur some calibration loss. I was just wondering if you could cleave apart why that might be the case.
No, I think you're right. It does incur calibration loss. It's just that calibration loss is incredibly easy to fix.
Is it something like you could have some uniform shift from, like, the calibration wouldn't change if there was some uniform shift across?
No, I think maybe what's behind my comment is that standard practice of machine learning tends to create calibration error because, well, standard practice, modern practice of machine learning is basically overfit your training set, interpolating networks, all kind of, and when you do this, in theory, in perfect theory, your machine learning minimizes expected strictly proper scoring rules. So in theory, you should get as close as possible to P of y given x. But in practice, what we're doing is that we're under-regularizing it. And so we're not minimizing expected proper scoring rule, we're minimizing an empirical one. And because we're under-regularizing it, we're minimizing it too much, so our probabilities go too far, close to 1 and zeros. And so in practice, the practice of machine learning gives you decalibrated predictors. And so it's somewhat well characterized that one thing that works well is then you recalibrate them. But it's really something that is focused on the calibration direction. There's a specific direction where we went too far. So, I mean, there is some grouping error if you're not in the distribution shift setting, but it's not too bad. Now, if you're in the distribution shift setting, it can be really nasty. Also, a typical machine learning paper doesn't worry about this, because typical machine learning paper assumes that the user is a competent machine learner with access to infinite compute power, and Hansen is in the setting where the user is fitting the actual data. And that's, I think, is an incorrect assumption.
Other questions?
Yeah, thanks for your talk. So you showed that under distribution shift, these models can get quite poorly calibrated, especially like when they're very confident. And many of the calibration procedures tend to involve some sort of updating, like temperature scaling, et cetera, based on like this new distribution. And if we're going to do that, we might as well also potentially fine-tune our model on these other distributions. And if we go ahead and fine-tune on these other distributions, do we still see these issues with calibration?
Right, so that's a good question. So actually these days, I would like us to make no difference, but we would need to write this paper on recalibration, fine-tuning, or stacking. As far as I'm concerned, those are just three kind of post-tuning, post-training, and they're all legitimate. It's just that recalibration is a very easy way of post-training, especially like temperature scaling. You've boiled down your problem to a 1D problem. You don't need many samples. It's also not very computationally expensive. You can, but I agree with you that it's just a special case. Now, what we found in the second paper, and maybe it wasn't obvious enough in what I was saying, is that this special case is actually really important. It gives you a lot. But yeah, That's just one case of post-training.
I have also perhaps like an unfairly hard question. I don't know if anyone knows the answer to this, but why does temperature scaling work so well? Like it's a special case of flat scaling where you would have a bunch of different hyperparameters for sort of recalibrating your model. It's not obvious to me that a single global temperature parameter would be successful in providing good calibration, yet it seems to be empirically very successful, at least for image classification. I was just curious if this is something you...
I think it goes back to the answer I gave just before, is that there's actually a specific setting of calibration error that we get in machine learning, in particular in vision, where we overfit the training set, which is really, you know, we've gone too far and we've screwed the scaling in the last layer. And this is exactly what temperature scaling does. And I don't know that temperature scaling is as useful on things like gradient boosted regression trees. We should check. We've just included it in scikit-learn, so now we can easily check.
I have more questions, but I'll let others ask.
We can take it offline.
Thanks for this really great talk. So I appreciate you talked about utility and decision theory and all of that, but you know, I think it's hard for people to justify, you know, a given utility function. At the same time, you didn't really talk about how calibration procedures affect things like accuracy, which is something that people really care about. And we tend to observe that kind of classifiers that are better calibrated tend to be less accurate. Can you comment on that?
Yeah, I think your question is really interesting because accuracy, I'm not talking about AUC, accuracy implicitly makes choices on utilities. And if people really care about accuracy, then they should really care about utility. Now, I know it's a conversation we're not having, both in academia and in industry. Actually, it's slightly easier to have it in industry. But if people come to me and say, what I really care about is accuracy, and they're not willing to define any kind of usage scenario where they're going to have a cost for decisions one way or another, I don't trust them. And I work a lot in healthcare, and I don't trust it at all. Now, if you're talking AUC, it's a different thing. But accuracy implicitly actually should be anchored in a utility thinking. My opinion.
So with this, we will close the session. Online questions. So
Online questions.
we are going to ask if there is some
I don't know how to
online
do this.
question. Yeah.
It's automatic.
It's automatic.
Anyone online?
Anyone online could ask some question. You want to intervene? Do not hesitate.
We have one guest.
Okay, I think there is no question online. So again, thank you very much.
Thank you.